Welcome back to another lesson in MCV4U. Today we'll be looking at the intersection between three planes. So here, when we look at the points of intersection of three planes, is related to the solution, again, or solutions of the following system of equations, which is really just looking at, again, the point of intersection that occurs between the three planes. And the three planes are all represented by this equation of ax plus by plus cz plus d is equal to 0. And then the subscript just again here represents the different equations. So for example, plane 1 has a1x plus b1y plus c1z plus d is equal to 0. Whereas again for plane number 2, it's again a2x plus b2y plus c2z plus d is equal to 0. And then for plane number 3, we have here a3x again plus b3y plus c3z plus d3 is equal to 0. Okay, so there's a couple of cases that we should look at here in terms of determining, again, what the point of intersections are between these three points. So here, if we look at these systems to start, these are what we call consistent systems. The reason we call these consistent systems is because they all have at least one point of intersection. So if we look at case 1, we see that here, again, the two planes pinwheel, but one is in a different direction. So again, two planes pinwheel, but one is in a different direction. There is no parallel normals or planes. So no parallel normals or planes. And here there is just one unique point of intersection, and that's at point P here. In this second case, so case 2a, then we get this pinwheel shape. So we get this pinwheel shape. Again, there is no parallel normals or planes. And here we see we have a line, again, is the intersection of three planes. And so here we see that there would be infinite point of intersections along a line. So infinite point of intersections along a line. In case 2b, again, L is the line of intersection of two coincident planes and a third plane not parallel to the coincident planes. So here again, we have two planes coincident, one plane not parallel. And here, there is again infinite point of intersection along a line. And finally, the last case here, in terms of the consistent systems, is the three planes are coincident. And here that means that there's infinite point of intersections along a plane. Okay. And here, if we look at these down here, these are what are called inconsistent systems. And they're called inconsistent systems because there is no points of intersection. And so here, when we look at this first one, you see that this represents kind of the shape of a triangle. And so the planes kind of develop this triangle here. And again, the planes and normals are not parallel. So planes slash normals are not parallel. Again, no point of intersection here. And when we look at here, the two planes are parallel but distinct. So here, two planes parallel but distinct. And again, then one plane is just non-parallel. And so here, again, no point of intersection. And then this last one here, three parallel but distinct planes. Three parallel but distinct planes. And so here, all of these inconsistent systems in these examples have no points of intersections. Okay, so we'll look at these equations and we're going to solve for, again, substitution and elimination, using substitution and elimination. And we're going to use that to solve the system. And there's this process that we follow. So the first example is the process. The first thing to do is to multiply up equations so one variable has a common coefficient, then compare the scalar multiples of the normals slash equations to narrow down possible cases. Again, state any observations and draw the geometric image if possible. Second is to solve the system of equations. In many cases, you will need to isolate the variable in one equation and sub into the other two, then substitute slash eliminate with their simplified versions. And then three, can make final conclusion and draw geometric drawing if not already completed. Alternatively, as we looked previously, you can use the Gaussian elimination to solve a system of equations. But this lesson will focus specifically on substitution and elimination. Here, if we look at example one, it says solve the following system of equation. Give a geometric interpretation of the solution or solutions. So here we have x plus y is minus z is equal to 1. X plus y plus z is equal to 2. And negative 2x minus 2y plus 2z is equal to 3. Here, what we'll do is we're going to make this x value to 2. So that means we'd have to multiply this first equation by 2, the second equation by 2, and the third equation by negative 1. And so here we get 2x plus 2y minus 2z is equal to 2. Second equation, we get 2x plus 2y plus 2z is equal to 4. In our last equation here, we get 2x plus 2y minus 2z is equal to negative 3. So here, what we notice in terms of our equations is that plane number 1 and plane number 3 are parallel yet distinct. And then plane number 2 is non-parallel. So here, if we looked at our drawing, okay, it looks something like this, and two parallel, and then one parallel. So plane one, plane three, and plane two. And this follows our idea of the inconsistent systems. So here, therefore, there's no point of intersection. Okay, the next one here looks at solving the following system equations and give a geometric interpretation of the solution or solutions. So you have x minus y plus z is equal to 1. We have x plus y plus 2z is equal to 2, and x minus 5y minus z is equal to 1. So here we see that if we look at the equations, none of these are parallel. None are parallel. If none are parallel, we can have, again, three possible solutions. Again, we can either have no points of intersection, we can have one point of intersection, or we can have infinite point of intersections. And so here, if we isolate our equation, our first equation here, we get x is equal to y minus z plus 1. And so here for plane number 2, if we sub that into our equation, we get y minus z plus 1 plus y plus z is equal to 2. Here, when we simplify, we get 2y plus z is equal to 1. Here, if we look at plane number 3, we sub that in, we get y minus z plus 1 minus 5y minus z is equal to 1. And so that will give us negative 4y minus 2z is equal to 0. Okay, so here, if we take our equations, so here if we take equation plane of plane 2, and we multiply that by negative 2 here, and we'll bring this equation of equation number plane 3. And so here we have negative 4y minus 2z is equal to negative 2. And we have negative 4y minus 2z is equal to 0. Okay, so here we see that if we subtract, again, the 2, we see that we get 0, and 0 is equal to negative 2. And so here, again, therefore, no points of intersection. And here the diagram will look like this. So here there's plane 1, plane 2, and plane 3. Okay, example 3 says solve the following system of equations. Again, give the geometric interpretation of the solutions. So here we have x plus 2z plus 3, x plus 2y plus 3z is equal to 1, 2x plus 4y plus 6z is equal to -1, and negative x minus 2y minus 3z is equal to 3. So here, if we take our first equation, multiply that by 2, again, we're going to try to make x equal to 2. Here, this second plane equation will just keep the same. And then the third equation will multiply by -2. And so here we get 2x plus 4y plus 6z is equal to 2. Second equation, the same, doesn't change. And then last equation we have is 2x plus 4y plus 6z is equal to -6. And so here what we see is they are all parallel, yet distinct. Again, constants are all different, but their normal is the same. So therefore, there is no point of intersection. And here we see that they are all parallel, but all distinct. Example number 4 says to solve the following system of equations and give a geometric interpretation of the solution. Again, here we have x plus 2y plus 3z is equal to 1, 3x plus 6y plus 9z is equal to 3, and -2x minus 4y minus 6z is equal to 2. So here for our first equation, we're going to multiply by 6. So again, to get the x values the same. Second equation here, multiply that by 2. And last equation here, we'll multiply by -3 to get the x value to be 6. So here we have 6x plus 12y plus 18z is equal to 6. Second equation, we have 6x plus 12y plus 18z is equal to 6. And our last equation here, we have 6x plus 12y plus 18z is equal to -6. So here, what we see is, again, we have plane 1 and plane 2 are coincident. Then plane 3 is parallel yet distinct. So here, again, that means no point of intersection. Here, that means that that line is plane 1 and plane 2, and this line is plane 3. This next question here is x plus z, or x plus y minus z is equal to 2, x minus 2y plus z is equal to 4, and the last equation is 2x minus 4y plus 2z is equal to 8. And so here, what we want to do is we'll take this last equation and we will divide it by 2 to get the x values the same in terms of the coefficients. So here we have x minus 2y plus z is equal to 4. Here what we see is that plane 2 and plane 3 are coincident. So plane 2 and plane 3 are coincident. And plane number 1 is non-parallel. Okay, so here means is that it looks like this. So here this is plane 2 or plane 3, and this is plane 1. And so therefore there will be a line of intersection. And so here we have for plane number 1, we have our equation. We'll isolate for x, x is equal to negative y plus z plus 2, and we'll sub that into our plane number 2 and plane number 3 equations. So here that's negative y plus z plus 2 minus 2y plus z is equal to 4. Here we isolate, we get negative 3y plus 2z is equal to 2. For plane number 3, sub again our x value into where the x's are. So here we have 2 times negative y plus z plus 2 minus 4y plus 2z is equal to 8. So that gives us negative 2y plus 2z plus 4 minus 4y plus 2z is equal to 8. And then if we simplify that, we'll get negative 6y plus 4z is equal to 4. And so here we'll take our two equations. Take this equation of negative 3y plus 2z is equal to 2. We'll multiply that by 2. And so here we have negative 6y plus 4z is equal to 4. And at the second equation, we have negative 6y plus 4z is equal to 4. And so here we see that 0, 0 is equal to 0. And so therefore, there is infinite points of intersection on the line. And so here what we'll do is we will now isolate one component to make a parameter. So here, isolate one component to make a parameter. So here we have 4z is equal to 4 plus 6y. And so z is equal to 1 plus 3 over 2y. Here we'll let y is equal to t. And so therefore z is equal to 1 plus 3 over 2 t. And here we have this is equal to negative t. So again, subbing the values in, negative t plus 1 plus 3 over 2t plus 2. And so x would be equal to 1 over 2t plus 3. Okay. Therefore, x is equal to 1 over 2t plus 3. Y is equal to t, and z is equal to 3 over 2t plus 1. Right here, I'm going to take these and we're just going to multiply up. We're going to multiply up this value here. So therefore, our line of intersection will be x is equal to plus 3, y is equal to 2t, and z is equal to 3t plus 1. And here, again, t is an element of real numbers. Okay, example number 6 here says to solve the following system of equations, and then I can give a geometric interpretation of the solution. So here we have x minus 2, y plus z is equal to 1, 2x minus 2y minus 4z is equal to 2, minus 4z is equal to 2, and we have negative 4x plus 4y plus 8z is equal to negative 4. So here for the first equation, we're going to take that and multiply that by negative 4, take our second equation, multiply that by negative 2, and keep the third equation. So here we have, again, negative 4x plus 4y plus 8z is equal to negative 4. Second equation we get is negative 4x plus 4y plus 8z is equal to negative 4. In our last equation here, we get negative 4x plus 4y plus 8z is equal to negative 4. So here these are, again, all coincident. And so here they pretty much can just be those 3 lines there. So this is plane 1, plane 2, plane 3. So again here, therefore, there's infinite point of intersections along the plane. And so what we need is an equation of the plane in parametric form. So here, yeah, x is equal to y plus 2z plus 1. We'll let y is equal to t, and z is equal to s. So here the plane of intersection will be therefore equal to x is equal to t plus 2s plus 1, y is equal to t, and z is equal to s, where t and s are an element of real numbers. Okay, and then this last one here, we have x minus 3y minus 2z. or sorry, the second last one. So here we have x minus 3y minus 2z is equal to -9, and 2x minus 5y plus z is equal to 3, and -3x plus 6y plus 2z is equal to 8. So here in our first equation, we're going to multiply by 6. Second equation, we are going to multiply by 3. And our third equation, we are going to multiply by 2, or sorry, by -2. And so here we get 6x minus 18y minus 12z is equal to -54. Here, the second equation here, we get 6x minus 15y plus 3z is equal to 9. And our last equation here, we get 6x minus 12y minus 4z is equal to -16. So here we see that, again, none are parallel. So none are parallel means that there's 3 possible cases. So here we have x is equal to 3y plus 2z minus 9. We'll sub that into our plane 2 equation. So we have 2 times 3y plus 2z minus 9 minus 5y plus z is equal to 3. That gives us 6y plus 4z minus 18 minus 5y plus z is equal to 3. So here we get y plus 5z is equal to 21 when we simplify. For plane number 3, sub again in that x. So -3 times 3y plus 2z minus 9 plus 6y plus 2z is equal to 8. Here we get -9y minus 6z plus 27 plus 6y plus 2z is equal to 8. And here we get -3y minus 4z is equal to -19. So here we have our two equations. Here for the first equation, we will multiply this by 3, and so that will give us 3y plus 15z is equal to 63. And in our other equation, we have -3y minus 4z is equal to -19. Here we'll get 11z is equal to 44. So here we're adding the two equations. 11z is equal to 44, where that means that z is equal to 4. Okay, so here we can set that back into our equations. We have y plus 5 times 4 is equal to 21, and therefore y is equal to 1 here. And then for x, we have x is equal to 3 times 1 plus 2 times 4 minus 9, and therefore x is equal to 2. So here, again, there would be a single point of intersection at 2, 1, and 4. So that would look like something like this. This is plane 1, this was plane 2. and this would be going to be here. Okay, example number 8 here gives us x plus y plus 2z is equal to -2, 3y minus y plus 14z is equal to 6, and x plus 2y is equal to -5. Here we'll take our first equation and multiply that by 3. Keep the second equation the same, and multiply the third equation by 3 as well. So first equation, what we'll have is we'll have 3x plus 3y plus 6z is equal to -6. Second equation here, we have 3x minus y plus 14z is equal to 6. And our last equation is 3x plus 6y plus, again, here's 0z is equal to -15. Here we see again, none of them are parallel. And therefore means there's 3 possible cases. Here we have, if we isolate for x here, we have x is equal to -2y minus 5, taking that from the third plane equation. So here in plane number 1, we have -2y minus 5 plus z plus 2z, or plus y plus 2z is equal to -2, -y plus 2z is equal to 3. And here in our second plane equation, we have 3 times -2y minus 5 minus y plus 14z is equal to 6. If we expand, we get -6y minus 15 minus y plus 14z is equal to 6, which will leave us with -7y plus 14z is equal to 21. Here we'll take our first equation and we'll multiply that by 7, and we'll keep the second equation here. And so our new equations here will be -7y plus 14z is equal to 21, and -7 plus 14z is equal to 21. So here again we see that so here we see there's going to be infinite point of intersections. And so again along a line. So here we have our diagram here. So we have plane 1, plane 2, and plane 3, and our line. So here, put into the parametric equation, so we have 2z minus 3 is equal to y, and we'll let z is equal to t, y is equal to 2t minus 3, x will then equal to -2 times 2t minus 3 minus 5, which is equal to -4t plus 1. And so again, therefore, infinite point of intersections along the line x is equal to -4t plus 1, y is equal to 2t minus 3, and z is equal to t. And here again, t is an element of real numbers.